Oh, it smells better in here.
Got the window open and
Right.
haven't blown the blower.
We all have to do these this year. It's 10 days. You just take your temperature, mark it down. I haven't had any symptoms. Sign it. We'll turn it in when we arrive. Okay?
Okay, so do I have to take the students' temperatures?
No. That's all on them.
Okay.
Their sheet, y'all, their first period teacher takes it anyway. They can just write it down and then they can take it home. This is all on them. That is not on you at all. Just you is on you.
Yeah.
All right?
Gotcha. Thank you.
Are y'all gonna behave? No, Riley, okay? Hey. I didn't see him do it first. You need to make better choices. Red heads don't hit one another.
This has separate symbols.
Does she really? Getting on her?
It says the same symbol as
She's
that.
on her
This is
now.
the same
Don't go by their colors, go by their names. We only had 4 colors to choose from.
So this separate symbol, this separate symbol, this separate symbol, this
Separate,
symbol.
separate, and then these separate.
Talk about ginger power.
It's like raising the undead.
Okay, I
Just start running at you. What to do? Look at me rocking and rolling.
Trying to get a video
That's the
going.
curve, kids. All right, y'all be nice to your teachers. Oh, what can we do with that? Can we seesaw?
Yeah.
Seesaw.
It really needs to be higher up. It's like, do I just put them right here?
Huh?
This is the 2.3 and the 2.3.
Okay, great.
All right, guys, see y'all later.
Bye. Okay. And Olive. Okay. I'm getting the video set up. Y'all can. Yes. Oh, that's not what I wanted to do. Everybody have a seat in your appropriate chair with appropriate posture. Or you will be stricken, smited, smoke.
Smoke. 6 feet on the floor.
6 feet on the floor.
Yeah. Nope.
The chair's got 4. 4
Yeah.
plus 2 is.
He's in pre-cal, he knows. Maybe.
That boy just ain't right.
I like it. Okay, here we go. Chemistry went overtime, so I'm a little behind here. Okay, let's see what we got. Plug it in.
Oh, by the way, where were you? Were you going outside today?
Yeah.
Okay.
Okay.
I haven't eaten in 20 I know. Dude, I'm kidding. Jeez. Huh?
Ding dong. Oh, you hear the ding dong? I made it. I said it so we could hear when she. Hi. You went ding dong because I said it for that. Now I'll know when you're there. Okay. So I'm going to share the screen. Actually, we're going to do something a little bit different. I am going to share the screen. We're going to do a little quiz and then we will watch a video. Well, on your whiteboard, informal. Don't freak out. my lady. And people are turning in work, I see, that's good. We need to erase. Okay, so what is I equal to? You write it down. Not quite, not quite. No,
No.
not quite. Ow, better, almost. Yeah. Okay, some people have been putting -1, and somebody put square, the negative square root. It's square root of -1.
I was like,
You don't put your board up yet. There's more to come.
I was like, where's the equation? I think we were talking about that.
This is imaginary number, okay? We'll put that. We're gonna see that a video on how they are not, well, they're called imaginary, but they're real. Okay, so what is I squared? And what is I cubed equal to? And what is I to the 4th equal to? And we'll go one more. What is I to the 5th equal to? I'll give you some time to ponder. And the final question is there a pattern? She would be asking. Come on, I don't know how to multiply things. Move it up to the 5th. What about the 2nd, the 3rd, the 4th, the 5th? Track. Getting every 4. Okay, let's erase my question marks here. What the heck? Okay, here we go. And then I'm gonna go back to that. Okay, so I to the 1 power is just I, right? And it's equal to square root of -1. And if you square that, if you square the square root of something, what happens? Yeah, if you square this, the square undoes the square root, and so you have -1. And then if I take I squared -1 and multiply it by another I, what happens to something when you multiply it by -1? It becomes negative, right? And so I cubed would be -1 times I, which is -I. What about I to the 4th? That'd be like I squared, right? -1 times -1? +1. And what about I to the 5th? You have like I to the 4th times I. What's 1 times I? Yeah, which is just I again, right? In other words, you go from I, -1, -I, +1, and then it's going to repeat. I, and then I to the 6th would be -1. I to the 7th would be -I. And then so you have this is the pattern basically. I, -1, -I, +1. And then it repeats. Make sense? Kind of cool. Because usually you think of multiplying a bunch of things, you get bigger and bigger and bigger and bigger, right? But instead, this is more cyclical. And you're going to kind of see why that is that way. So now I'm going to stop sharing this, if I can figure out how to do that. Okay. And I'm going to share something else. Okay. And we'll get Eddie to turn the middle light switch off. But let me check with Candace. Candace, can you see this screen? It has f of x equals x squared plus 1.
Yes, ma'am.
Okay, so sit back, get your popcorn, relax. We're gonna watch you do these. Here we go, and play.
Let's say we're given the function f of x is equal to x squared plus 1. We can graph our function and get a nice parabola. 2r1 is equal to 0.
Okay, I paused it because I wanted to see if Candace is hearing the sound.
Yes, ma'am. Thank you.
You hear the guy talking?
Yes, ma'am.
Okay, I'm gonna back it up a little bit. Okay. Can y'all hear it?
Yes.
Is it over there than this? Okay.
Let's say we're given the function f of x is equal to x squared plus 1. We can graph our function and get a nice parabola. Now, let's say we want to figure out where the equation equals 0. We want to find the roots. On our plot, this should be where the function crosses the x-axis. As we can see, our parabola actually never crosses the x-axis. So according to our plot, there are no solutions to the equation x squared plus 1 is equal to 0. But there's a small problem. A little over 200 years ago, a smart guy named Gauss proved that every polynomial equation of degree n has exactly n roots. Our polynomial has a highest power or degree of 2, so we should have 2 roots. And Gauss's discovery is not just some random rule. Today we call it the fundamental theorem of algebra. So our plot seems to disagree with something so important, it's called the fundamental theorem of algebra, which might be a problem. What Gauss is telling us here is that there are 2 perfectly good values of x that we could plug into our function and get 0 out. Where could these 2 missing roots be? The short answer here is that we don't have enough numbers. We typically think of numbers existing on a one-dimensional continuum, the number line. All our friends are here. 0, 1, negative numbers, fractions, and even irrational numbers like root 2 show up. But this system is incomplete. And our missing numbers are not just further left or right. They live in a whole new dimension. Algebraically, this new dimension has everything to do with a problem that was considered impossible for over 2,000 years, the square root of -1. When we include this missing dimension in our analysis, our parabola gets way more interesting. Now that our input numbers are in their full 2-dimensional form, we can see how our function x squared plus 1 really behaves. Our function does cross the x-axis. We were just looking in the wrong dimension. So why is this extra dimension that numbers possess not common knowledge? Part of the reason is that it has been given a terrible, terrible name. A name that suggests that these numbers aren't even real. In fact, Gauss himself had something to say about this naming convention.
So you have to read it yourself. But it's been called direct, inverse, lateral instead of positive, negative, and imaginary. They're much better. So instead of imaginary numbers,
so yes,
lateral
our
numbers.
missing dimension is comprised of numbers that have been given the ridiculous name imaginary. Gauss proposed these numbers should instead be given the name lateral. So from here on, let's let lateral mean imaginary. To get a better handle on imaginary, I mean lateral numbers, and really understand what's going on here, let's spend a little more time thinking about numbers themselves. Early humans really only had use for the natural numbers, that is 1, 2, 3, and so on. This makes sense because of how numbers were used. So to early humans, the number line would have just been a series of dots. As civilizations advanced, people needed answers to more sophisticated math questions, like when to plant seeds, how to divide land, and how to keep track of financial transactions. The natural numbers just weren't cutting it anymore, so the Egyptians innovated and developed a new high-tech solution, fractions. Fractions filled the gaps in our number line and were basically cutting-edge technology for a couple thousand years. The next big innovations to hit the number line were the numbers 0 and negative numbers, but it took some time to get everyone on board. Since it's not obvious what these numbers mean or how they fit into the real world, 0 and negative numbers were met with skepticism and largely avoided or ignored. Some cultures were more suspicious than others, depending largely on how people viewed the connection between mathematics and reality. And this is not all ancient history. Just a few centuries ago, mathematicians would intentionally move terms around to avoid having negatives show up in their equations. Suspicion of 0 and negative numbers did eventually fade, partially because negatives are useful for expressing concepts like debt, but mostly just because negatives kept sneaking into mathematics. It turns out there's a whole lot of math you just can't do if you don't allow negative numbers to play. Without negatives, simple algebra problems like x plus 3 equals 2 had no answer. Before negatives were accepted, this problem would have had no solution, just like we thought our original problem had no solution. The thing is, it's not crazy or weird to think these problems have no solutions. In words, this algebra problem basically says, if I have 2 things and I take away 3, how many things do I have left? It's not surprising that most people who have lived on our planet would be suspicious of questions like this. These problems don't make much sense. Even the brilliant mathematicians of the 18th century, such as Euler, didn't really know what to do with negatives. He at one point wrote that negatives were greater than infinity. So it's fair to say that negative and imaginary numbers raise lots of very good, very valid questions. Like, why do we require students to understand and work with numbers that eluded the greatest mathematical minds for thousands of years? Why did we even come to accept negative and imaginary numbers in the first place when they don't really seem to be connected to anything in the real world? And how do these extra numbers help us explain the missing solutions to our problem? Next time, we'll begin to address these questions by going way back to the discovery of imaginary numbers.
We're going to see 6 of these, I believe. They're pretty short. Let's see, is it going to scroll on to the next one? Let me see if it does. Yes.
Last time, we left off wondering how imaginary numbers could help us find the roots of our equation x squared plus 1. And further, how imaginary and negative numbers even became part of modern mathematics after being avoided and ignored for a couple thousand years. Because, let's be honest here, they don't really make that much sense. But something happened in Europe around 5 centuries ago that would no longer allow mathematicians to ignore these numbers. An Italian mathematician, Scipione del Ferro, was trying to solve a problem not that different than ours. At some point, you've probably seen the quadratic formula. This formula is super useful because it gives us the roots of any equation with the highest power of 2. All you have to do is plug in A, B, and C, and out pops the answer. Del Ferro was trying to find a formula like this for equations with the highest power of 3, cubics. The general case is pretty tough, so Del Ferro first considered the case where the x squared term is missing and the last term is negative. In the 16th century, negative terms were way too sketchy to write, so Del Ferro wrote his cubic as x cubed plus cx is equal to d, and required c and d to be positive. Now that we have our equation set up, the game here is to get x by itself on one side and all the constants on the other side. This is pretty easy in linear equations. We can just add, multiply, divide, or subtract until we get x alone. Quadratics make this a bit harder. You may have learned how to solve these in school. It requires some cleverness and factoring by completing the square. Del Ferro was trying to do the same thing for his cubic equation, and through some clever substitution, he eventually found a solution. Whoa. Just like the quadratic formula, Del Ferro's new formula allowed him to find the solution to cubic equations by simply plugging in values. Now, for some reason, the way mathematicians earned money in the 16th century was through challenging other mathematicians to what were basically math duels. So Del Ferro kept his new formula a secret to use in his next duel. What happens next is a bit of a long story. Here's the quick version. Del Ferro kept his formula secret until he was on his deathbed when he finally told his student Antonio Four. Four immediately thought he was invincible, or at least invincible in a math duel, and challenged a way more skilled mathematician, Fontana Tartaglia, to a duel. Tartaglia had already claimed he could solve cubic equations like this, but had actually been totally faking it. Tartaglia freaked out before the math off and actually figured out how to solve these equations at the last minute and proceeded to completely dominate Fior. Tartaglia then went on to share his formula with the world. Not really, he kept it super secret so he could keep kicking butt in math duels. That is until a very talented mathematician named Cardon heard about the formula and pressured Tartaglia to share. He eventually went along, but only after Cardon swore to an oath of secrecy. Fortunately for us, after Cardon came across the surviving work of the original discoverer, Del Fierro, he figured that it wasn't such a big secret and published the formula in his book Ars Magna. Cardon went on to improve his borrowed formula, even making it work for cubics that included an x squared term. However, along the way, Cardon came across a problem. In a slightly different version of the equation, written as x cubed equals cx plus d, under certain values of c and d, the formula would break. Let's take the innocent-looking equation x cubed equals 15x plus 4. When we plug into Cardon's formula, we get a result that involves the square root of negative numbers. The square root of a negative number created enough of a problem to stop Cardon in his tracks. Square roots ask us to find a number that, when multiplied by itself, yield the number inside the root sign. The square root of 9 is 3 because 3 times 3 is 9. Importantly, the square root of 9 is also negative 3 because negative 3 times negative 3 is also positive 9. But what about the roots of negative numbers? What is the square root of negative 9? Positive 3 won't work, and neither will negative 3, so we're stuck. Cardon was stuck too. He didn't know of any numbers that, when multiplied by themselves, resulted in a negative. Now, this certainly wasn't the first time the square root of a negative had shown up. Usually mathematicians would interpret this as the problem's way of saying there are no solutions, and in many cases this is true. However, in this case, we know there is at least one solution because of the way cubics are shaped. Regardless of their coefficients, cubic functions will always cross the x-axis at least once, meaning that our equation, x cubed equals 15x plus 4, will have at least one real solution. So what we have here is a problem that must have an answer, and a formula that has been proven to work. But when we put these together and try to solve the problem with our formula, we quickly arrive at what appears to be the impossible: the square roots of negative numbers. Sometimes when things break in math and science, it means just that, they're broken. But there are other more interesting situations in which broken mathematics gives us the keys to unlock new insights. The way in which Cardon's formula was broken turned out to be incredibly important to mathematics and science, and that's what we'll discuss next time.
Little break. They have a workbook. I want to get it. I think I can get the online version.
We left off last time with Cardon and his broken formula for finding the roots of cubic functions. Cardon knew that his problem had to have a solution, but didn't know what to do with the square roots of negative numbers that kept popping up in his equations. Cardon came close to finding a way to make his formula work, but got stuck in an algebraic loop where a bunch of work would just lead him right back to where he started. It took one more generation of mathematicians to get to the bottom of this. Cardon's student, Raphael Bombelli, made some incredible insights about what's really going on here. Let's remember why Cardon was stuck. The square roots of negative numbers ask us to find a number that, when multiplied by itself, will yield a negative. Neither positive nor negative numbers will work.
Flashback.
Bombelli's first big insight was simply to accept that if positive numbers won't work and negative numbers won't work, then maybe there's some other kind of number out there that will. Now, if there is some other kind of number out there, a good follow-up question is, what are we going to call it? After all, we need to use it in our equations. Bombelli's approach was a very practical one. Rather than dream up a new name and symbol, Bombelli simply let the square roots of negatives be their own thing. In the past, mathematicians would have thrown in the towel here and declared the problem impossible. But Bombelli was able to press on simply by allowing the square roots of negatives to exist. Let's take a simple example of our new numbers, the square root of negative 1. For being a new kind of number, it doesn't look very exciting. It might kind of seem like our old numbers. But remember, it does have the exact special property we need. When we square it, the result is negative. Further, since our number doesn't behave like a positive or a negative, it must be something new. Now, if this all seems a bit fishy to you, like a slightly too convenient algebra trick, you're in good company. In fact, it's hard to introduce imaginary numbers without them sounding like an arbitrary invention. However, before we dismiss the square root of -1 as some abstraction invented to torture students, let's review what we've learned so far. Cardon and Bombelli were genuinely stuck on a tough problem that they knew had a solution. What Bombelli was able to see is that if he extended the existing number system, as had been done so many times before, he could solve the problem. Just as people needed fractions, zero, and negative numbers to solve new problems in the past, to solve this problem, Bombelli now needed the square root of -1 to be its own brand new number. Let's make sure we're clear about what it means for the square root of -1 to be its own number. If our new number is truly a discovery and not an invention, it should behave like the other numbers we already know about. It should follow the established rules of algebra and arithmetic. And it turns out the square root of -1 does, for the most part. Just as we can split apart the root of the product of two positive numbers, we can also split apart the square roots of negatives. The square root of -25 splits into the square root of 25 times the square root of -1. This process is important because it allows us to express the root of any negative using the square root of -1. The square root of -25 becomes 5 times the square root of -1. We can use this process to expand the root of any negative number, writing it as some number we already know about times the square root of -1. Let's quickly make sure that our new numbers follow the same algebra rules as our old numbers. In algebra problems with x, only like terms can be added and subtracted. 2x plus 3x is 5x, but 2 plus 3x is just 2 plus 3x. Likewise, 2 square roots of -1 plus 3 square roots of -1 is equal to 5 square roots of -1. But 2 plus 3 square roots of -1 is just 2 plus 3 square roots of -1. Finally, unlike terms can be multiplied, just as in algebra with x. 5 times x is just 5x, and 5 times root -1 is just 5 roots of -1. Now, there are some cases where our new numbers behave a little strangely, but these can often be avoided by first separating out the square root of -1. Now that we have a grasp on how our new numbers work, we can see how they fix one of our problems from last time. We now have a strategy for dealing with the roots of negatives. We can evaluate the square root of -9 we were stuck on and obtain 3 times the square root of -1. All this is important, but it isn't enough to solve Cardon's problem. We still need to figure out how to deal with the cubed roots of these numbers. Bombelli was able to solve our problem through one more powerful insight, and that's what we'll discuss next time.
Hanging in there? Kind of cool? This next one, number 5, number 4.
Last time, we decided to let the square root of -1 be its own new type of number, hoping it would help us solve Cardon's problem. Doing so is helpful, but finding a solution requires one more insight from our friend, Raphael Bombelli. Bombelli knew that because of the way cubics are shaped, our function had to have a solution that didn't involve the square root of -1. It had to be a plain old regular positive or negative number, as he had seen before. His second big insight here was that for this to be the case, the root of -1 parts of each half of the equation must cancel out when added together. Bombelli used this idea to equate the two parts of the equation to a plus b times the square root of -1 and a minus b times the square root of -1, where a and b are constants that we need to find. To solve, we can first eliminate that annoying cubed root by cubing both sides. The result is a particularly tough system of equations. Bombelli was able to get around this through some clever guessing and checking. If we look at our original equation and test a few integers, we eventually see that 4 is a solution. If we substitute 4 into our new equations, we can solve for a and b and obtain a equals 2 and b equals 1. These values make the two parts of our expression equal to 2 plus the square root of -1 and 2 minus the square root of -1. We can cube these and show that they are in fact equivalent to what we started with. And more importantly, when we add the two parts, as the formula tells us to do, we just get 4, which we know is a solution to our original equation. We have found the solution to Cardon's problem. And what's really interesting is that our problem had nothing to do with the square root of -1, and neither did our answer. However, along the way, we found that by extending our number system to include the square root of -1, we were able to find a solution. And it turns out that extending our number system in this way is helpful in lots and lots of other problems as well. So what did Bombelli do to celebrate after discovering a number so crucial to the future of science and mathematics? He actually did nothing. He discounted his discovery and basically said it was a hack. As ridiculous as that might seem now, Bombelli drew a pretty reasonable conclusion at the time. It just seemed a little too convenient, like a trick devised just to solve problems like this. Squaring numbers had, up until that point, largely been associated with what the operation is named for, squares. A square's area is equal to the length of its side squared. So positive areas make sense. But what could a negative area be? What even is the square root of -1? Questions like these slow down the development of imaginary numbers. It turns out there is a much deeper and richer meaning lurking below the surface, but it would take long after Bombelli's death to be revealed.
Two more. And there's actually quite a few in this series, but I'm only going to take you up to a certain point, and then you're on your own after that. Continue if you want. I think it's to some pretty college,
We left off with
graduate college
Bombelli's
level.
discovery that if he allowed the square root of -1 to be its own number, he could solve problems that had been stumping mathematicians for decades. Despite the usefulness of his discovery, Bombelli and other mathematicians generally regarded it as a hack. After all, what could it possibly mean to take the square root of a negative number? Just like our friends 0 and negative numbers before, the square root of -1 was generally regarded with suspicion because it didn't correspond to anything people could think of in the real world. For this reason, the square root of -1 was given the terrible names imaginary or impossible. A century or so later, Euler began using the symbol I to indicate the square root of -1, making the algebra less clunky. Unfortunately, the name imaginary stuck around, and that's still what we call these numbers today. In response, everything on the original number line gets the name real. When we put together a real and an imaginary number, we obtain what we today call a complex number. What is remarkable about this time period is that although imaginary and complex numbers were used in calculations and derivations, the deeper meaning behind these numbers was left undiscovered for over 200 years after Bombelli's death. Before we dive into this deeper meaning, let's think about I algebraically for a moment. If we raise I to higher and higher powers, it doesn't get bigger as other numbers would. We know I squared is -1 from the definition, and if we keep multiplying I by itself, we see a pattern that repeats every 4 multiplications, over and over and over and over. Hold on to that fact for 90 seconds. Let's return to our friend the number line. Remember that all the numbers we know about show up here, except imaginary numbers. They are nowhere to be found. If we think back to our original problem with the roots of negative numbers, we can visualize this using the number line. Remember, the issue we had was finding a number that when multiplied by itself would yield a negative. To see this more clearly, we'll use arrows instead of dots to indicate numbers. Multiplying a positive by itself maintains direction on the number line. It stays positive. If we multiply by a negative, we flip directions or rotate 180 degrees. Squaring a negative lands us in the positive numbers because we start on the left side with our first negative and rotate 180 degrees when we multiply by the second negative. So there's no way to land on a negative number when squaring. A positive squared results in a positive, and a negative squared requires starting in the negative territory. And when we multiply by the other negative, we arrive back in the positive numbers. So what we need is something in the middle. A number that when we multiply by it only rotates 90 degrees, not 180 degrees as negatives do. This is exactly what imaginary numbers do. I squared is -1, meaning that the first I puts us 90 degrees from the positive real numbers, and multiplying by I rotates us 90 degrees further, exactly where we want it to be, firmly in negative number territory. Back to that fact you were hanging on to. Since multiplying by I corresponds to one 90-degree rotation, if we place our imaginary axis at a right angle to our number line, our algebra will perfectly fit with our geometry. If we start with the real number 1 and multiply by I, algebraically we get I, which geometrically corresponds to a 90-degree rotation from 1 to I. Multiplying by I again results in I squared, which by definition is -1 and again matches a 90-degree rotation from I. As we keep raising I to higher and higher powers, we keep rotating around with our values repeating every 4th power, just as they did algebraically. So the big insight here is that imaginary numbers do not exist apart from the real numbers, but right on top of them, hiding in a perpendicular dimension. This is the deeper meaning behind imaginary numbers. They aren't just some random extra number or hack. They are the natural extension of our number system from 1 dimension to 2. Numbers are 2-dimensional. And what's even more remarkable is that if we accept this, that numbers have a hidden dimension, we end up not only with a more complete mathematics, but with incredibly powerful tools for science and engineering. Next time, we'll show how and why thinking about numbers this way is useful.
That kind of looks like the unit circle.
Yeah, but it's not. You got one more, I think, right? That was 5. And so it starts getting really weird. I think you can handle this level.
Last time we arrived at an incredibly powerful tool in mathematics, science, and engineering, the complex plane. The complex plane is an extension of the number line where we include the imaginary dimension vertically. Just as we can plot xy coordinates on the xy plane, we can plot complex numbers on the complex plane. This arrangement is why Gauss preferred the term lateral over imaginary and inverse instead of negative. Gauss suggested that we should call the numbers to the right of the origin direct. The numbers.
Yeah. Okay. So I wanted to clear up names. When you have imaginary, when you have X and Y, you've got two real number lines, a real number line and another real number line. And you're just saying that a number on this number line is going to be associated with or matched with or paired with a number on this one. That's called a coordinate up there. 2 is related to 5 or whatever. Okay, but then on this one, it's the real numbers and then the imaginary numbers. So they're not the same. It's not the same coordinate system, but it's used similarly. Keep going. I think that should work.
To the left of the origin, inverse, and the numbers above and below the origin, lateral. Now that we've seen the complex plane, let's discuss why it's so powerful. We've seen two-dimensional planes before, where each axis represents a different quantity. In fact, we started our whole conversation with one. In a normal XY plane, there's no required connection between the dimensions, no rules about how they should relate to each other. On the complex plane, however, we have the rules of algebra with complex numbers we discussed earlier. These rules impose a very specific and useful relationship between the two dimensions. The first rule is how complex numbers add and subtract. The real and imaginary parts add independently, making complex numbers in the complex plane useful for problems involving motion in 2 dimensions. If we travel in one direction for a certain distance, and then in another direction, we can add the components of each part of our trip together to find the total distance we have traveled in each direction. So that's cool, but as you may already know, we can do the same exact thing with the vectors. Where complex numbers get really interesting is through multiplication. We can multiply complex numbers together by foiling, just as we do with binomials in algebra, with the minor complication that we know I squared can be replaced with -1. This is a perfectly valid algebraic solution to our problem, but is only half the picture. There's another equally valid way to think about multiplying complex numbers, and it has everything to do with the complex plane. Instead of just telling you what this interpretation is, it'll be way more fun to try to figure it out with some examples. To discover this deeper meaning for yourself, all you need to know is the following: how to multiply complex numbers algebraically, as we just did, how to plot numbers on the complex plane, the Pythagorean theorem, and finally, how to use arctangent to find angles. What's cool here is that if you're able to figure this out, you'll have discovered for yourself a super useful bit of math that was unknown to the smartest mathematicians on the planet until only 2 centuries ago. Next time, we'll uncover this interpretation of complex multiplication using the complex plane, and we're going to do it with 4 examples: 4 plus 3i times I, 4 plus 3i times 2i, 4 plus 3i times itself, and finally, 2 plus I times 1 plus 2i. Through considering each of these problems on the complex plane and looking at the patterns that naturally emerge, we'll arrive at the deeper meaning we're searching for. Do try this at home. You'll find a link below to the problem statement on the Welsh Labs blog. Even if you're already a boss at complex numbers, or if you have no idea what I'm talking about, I promise it's a valuable process. And we'll sort out all the details next time.
So I'm not going to make you do that. There. And okay, go back here. And we can play with that. And anything live. And what time is it? We got 7 minutes. So I don't have another video, and if you have more stuff to work on, you can work on it, but that's all I'm going to do today. Any comments or questions about it? I tell you, when you get into high-level math in college, and especially graduate level, it's all about the complex plane part, like so. these hypotheses that came to, oh, have you heard of the millennial, what's it called, millennial challenges or something? You heard of that?
Basically, they only exist because somebody was like, hey, I want to be able to nail these people to the ground in math challenges. And then he gets and he's like, you know, I'm not going to use this.
True, but now we wouldn't have electronics if it wasn't for imaginary numbers. And my son is, my middle son works for Spectrum, and he's a trainer, you know, for payroll people. And they use imaginary numbers all the time. It's amazing how much, and it's weird because they found out about them first through mathematics when it had nothing to do with the real world, and then later found out, oh yeah, it's the real world really, really good.
It shows up a lot in physics when you do wave mechanics,
Yeah,
but then it all reduces down to the real numbers anyway,
yeah.
because that's physical.
Uh-huh.
So, but when you're actually doing the wave mechanics math, it's all with imaginary.
And back in the late 20th century, they came up with, I forget how many, there were these questions in math that needed solving. And they were called millennial questions or whatever, or conjectures, I think. They had these different conjectures, and they had an award of $1 million if you solve or prove the conjecture to be true or false, then you get $1 million. And I think a few of them have actually been solved since the year 2000, but a lot of them are still there. And they nearly all, like the Riemann hypothesis, you're going to find out more about this guy named Riemann when you get into calculus. But it has to all to do with the imaginary plane. And have you heard of the Mandelbrot? Mandelbrot, what do you call it? Mandelbrot. I think it's fractals. You've heard of fractals?
I'm pretty practice.
Fractals. Mandelbrot set shows a weird, almost paisley-like looking system. They have some really cool. I don't know. I'll probably try to get it for you tomorrow. Patterns that they decorate. You can get it as wallpaper on the computer, and they actually have where you zoom in and you zoom in and you zoom in to this thing, and then it just keeps zooming in forever. And all of it comes from the complex plane and a very simple equation that reiterates over and over and over and over. So all this stuff is really pretty cool stuff. When you get to calculus and you think, wow, I've learned calculus next year. That's just barely scratching the surface of math.
Yeah, that's nothing.
Yeah, I was surprised with that. So anyway, I like when they pull that little thing up and you see that extra dimension. But it's actually like that. It was strange. And nowadays on videos, like, do you watch 3 blue, 1 brown videos? He does great graphics with this kind of stuff too. So what were you saying?
I was talking about Euler's formula earlier. So it's like the unit circle, but it's a different unit circle.
Ah.
And you can use imaginary numbers kind of intertwined with trigonometric identities.
Yeah, e to the pi I equals, no, minus.
E to the ix equals cosine x plus I.
Well, the simplified version of that. I think it's -1 equals, or plus 1 equals 0.
Yeah.
Something like that. And it, E and pi and I and 1 and 0 are like the 5 fundamental constants of math in this math land, you know. And yet there's one simple, like if you take an irrational transcendental number and raise it to an irrational transcendental number times an imaginary number and add 1 to it, you get 0. It transforms into
nothing.
Yeah, when they came up with this, they're like, what does it mean? I don't know. But people have tattoos with this. It's like the most beautiful thing in mathematics.
Yeah.
It's amazing. I don't know. I like math. I get excited about it. Okay, so y'all can go to lunch and we're gonna go outside. Sounds good. All righty. Any questions, Candace? They're scraping their chairs and I can't hear you.
I did have, I believe, about 5 questions, but I can email them to you.
Okay, is that on the review?
That is on the review, yes.
Yeah, why don't you email them to me and then I can like work them out or answer them and then send you pictures again.
Yes, ma'am. I did give them all a shot, so I do know what my questions are, and some of them I do have a shaky idea. I just need confirmation.
Yeah,
most part.
okay. And I emailed you the quiz, but I wrote on the subject line that it's the quiz for Friday. And so you can wait till Friday to open it, or you can go ahead and print it out, whatever, but it'll be due probably Monday, if that's all right.
Yes, ma'am. Thank you.
Thank you. Talk to you later.
Bye.
Bye.